So I will talk about Bohmian mechanics and cosmology. I kind of tie topics of the first week together with topics of the last week. I'm going to talk a bit about the measurement problem, possible solutions to the measurement problem, and how they could help in cosmology, solving conceptual problems, and maybe also practical problems. So the outline of the talk is as follows. So first, I'm going to give an introduction to Bohmian mechanics, addressing some of the questions I had the last couple of weeks. Then I'm going to go to quantum gravity, what Bohmian mechanics has to say in quantum gravity. Then I'm going to say something about semi-classical approximations to quantum gravity based on Bohmian mechanics, which is what I'm currently working on. And then finally, I'm going to say something about the quantum to classical transition in inflation theory, which came up in a discussion last week. So first of all, Bohmian mechanics. It's a theory invented by Rutgers in 1927 and rediscovered by Bohm in the 50s. And as you heard in the first week, it's a theory about point particles, actual point particles. So stuff like labels, chairs, these are made out of point particles. And the way they move is by this equation, called the guidance equation. The wave function appears in this guidance equation, so you also have the wave function, and the wave function is telling these particles how to move. It does it through this equation. So the wave function satisfies the usual Schrödinger equation, the guidance equation, how the particles move around under the influence of the wave function, given by this equation. And it just says that the velocity is basically 1 over the mass times the gradient of the phase. The phase is just defined by that equation. So here this is possible trajectories for the double slit experiment. So when you perform a double slit experiment and you fire one particle, one of these trajectories is going to be realized. Okay? So not all the particles have to go through the slits at the same time. No, there's one particle that's following one of these trajectories. And you see that the dynamics is such that particles tend to bunch up where you have interference peaks, and they try to avoid regions where you have destructive interference. Okay. And if you want to have agreement with standard quantum theory, what you need to have is that the final distribution is given by psi squared. Okay. And you know, the Bohmian laws are such that if you start from a distribution which is equal to psi squared at the beginning, it remains psi squared. Okay. So we're going to have psi squared distribution at the final detection screen, given that the distribution of particles over an ensemble is given by psi squared, and it goes through the screen. Okay. So you can see. So if you have psi squared distributions, you have agreement with quantum theory. If you have non-psi squared distributions, you have disagreement. For example, suppose all the particles, for some reason, just start out in the lower slit. Okay. Given that the wave function is still this superposition, if the particles start out in the bottom, they're going to stay in the bottom. They're never going to cause the symmetry down. So you're only going to have half of the interference pattern. So the special distribution is psi squared. It's called an equilibrium distribution. It's called quantum equilibrium. And you can show that the typical universe will exhibit quantum equilibrium. So in Bohmian mechanics, you don't have collapse of the wave function. So the wave function always evolves according to Schrödinger's equation. Okay. And we already saw now position distributions are given by psi squared in equilibrium, usual quantum distributions. There's another feature of the theory that something like collapse is an emergent phenomenon. And you have this collapse whenever you would expect collapse in usual quantum theory. Okay. How can you see that? Well, assume that your wave function is developing into a superposition of psi 1 and psi 2, and that these wave functions psi 1 and psi 2 have no common support. Okay, so here I've drawn this, the support of the wave function. So here the wave function is non-zero, and outside it's 0 or it has very low amplitude. And then support this support branches like that. What's going to happen with the configuration is it's going to either follow one or the other branch. If it follows this branch here, then this packet is going to have no effect anymore on the configuration. It's going to have no effect on the dynamics of this configuration. So for all practical purposes, you could just ignore this packet of the branch. So this is how collapse comes about. It's nothing fundamental. It's just in your description. If you want to ignore part of the wave function, you can do so if you have non-overlapping branches, or approximately non-overlapping branches. So another thing, there's a very natural definition for the wave function of a subsystem. So Goldstone already explained that. What is it? Well, suppose you have a composite system. So you have systems composed out of two subsystems, and the configuration variables are x1 and x2. So you have a wave function for that total system. You also have two configurations for that total system, x1 and x2. How can you define the wave function for system 1? Well, you take this wave function, psi, and you plug in the actual configuration at that time in the slot for the second particle. What you end up is just with a wave function of just first configuration variable and time. You can see the time dependence comes in from the usual time dependence of psi and of the configuration. So why is this a natural definition? Well, if you look at the trajectory of x1, well, it's going to satisfy this law of motion. So you can let the velocity be determined by just this wave function of the subsystem called conditional wave function, or you can let it be determined by the total wave function. So for that reason, it's a natural definition. And it's also this definition also corresponds with what we would use when we would describe, say, the double slit experiment. If you want to regard Bohmian mechanics as a universal theory, there's a universal wave function. Suppose you want to describe double slit experiment, you want to associate a wave function to the electron that goes through the slits. Well, this would be a natural definition for defining the wave function of the system going through the slits. And this wave function, well, you could calculate what equation is going to satisfy. It may or may not satisfy some Schrodinger equation. Okay? You just take a time derivative of that. It's either going to be equal to the Hamiltonian of some Hamiltonian acting on the conditional wave function or not. So you can calculate what's going to happen. And also, you have something where you have the collapse of this conditional wave function. So before I showed you, in some cases, in your description, you can forget about part of the packet. So this corresponds to some effective collapse. Here, this conditional wave function is actually going to undergo an actual collapse in certain circumstances. So when you do, for example, in the measurement situation, what the wave function is doing is going to actually collapse. So, Goldstone gave that as a homework. I'm not sure. I guess everybody did that. So this is just repeating what you already discovered by now. If you have the wave function of a system, in which you're going to do the measurement, then there's some sort of position of the eigenstates of the operator you want to measure. So I. You have a wave function of a measurement device, phi, and suppose that's the ready state. Okay. Total wave function is going to be this product, psi and phi. Here the measurement is going to evolve into the supposition. Psi, the eigenstates of the operator, phi I, the corresponding states of the measurement device. For example, the measurement device could be thought of as including some kind of macroscopic needle, pointing up in the ready state, and then pointing towards some angle corresponding to the result of the measurement. And the conditional wave function, if you calculate that, you'll find that it goes from So the conditional wave function for the system on which we measure is going to go from psi to one of these eigenstates psi I. And the reason for that is, and the reason for that is that these phi i's, well, these phi i's correspond to different states of the measurement device, different macroscopic states of the measurement device, and these are going to be typically non-overlapping. Okay. So if you calculate the conditional wave function for the system, you plug in here the actual configuration of the measurement device. So because these phi i's are not overlapping, most of these terms are going to be, well, all of these terms are going to be 0 except for one. Okay, so you plug in the actual configuration. Good. So you don't have a measurement problem in Bohmian mechanics, and it reproduces the quantum predictions in quantum equilibrium. What more can you do with theory? Well, there's a natural way to get to the classical limit. So you already have positions, so you already have particles, and I can see when this dynamics is approximately classical. Okay. And the thing to do is, well, you have the first order equation, just take another time derivative. Well, you get something that looks like Newton's equation, but with an extra potential, with Q. And this is called the quantum potential. So the Bohmian equation gives you Newton's equation plus an extra potential or with an extra force. And of course, you're going to get the classical limit whenever this extra force is negligible compared to the usual force. Okay. Like if you're interested in the classical limit of the microscopic system, relative to real freedom, you're going to be interested in, like, say, the center of mass, and you're going to study whether the center of mass is behaving approximately fast. The other property that's worth mentioning is that it's non-local. Okay. If you look at this equation of motion, the velocity of one particle is going to depend on the position of all the other particles. Okay. It doesn't matter really how far these other particles are away from this particle. Okay.
Does it depend a bit less on the ones that are further away? Is there a bit of locality?
There's no fall off of the non-locality. Like in an EPR state, an entangled state, if you remove one of the parties far away, it doesn't matter how far you remove them away.
But this isn't a phenomenon of Bohmian mechanics. This is a phenomenon of quantum mechanics. Right.
And I got the question a lot of times last week after David Albert's talk about non-locality that what's going on here? So this theory is non-local, but on the other hand you cannot use it to signal faster than the speed of light. So let me explain how that comes about in Bohmian mechanics. Yeah.
I just, from my own knowledge of quantum mechanics and interpretations thereof, I thought that like every key interpretation wasn't non-local. Is that incorrect?
Just a swing.
I'm sorry, I thought that the Everettian interpretation wasn't non-local, that it was in some sense local. Is that not
Well, that's
right?
kind of hard to judge.
Okay.
Because, yeah, maybe
I think there is at least one fairly precise sense in which Everett is not non-local in the way that the other interpretations are. On the other hand, you have to factor in, you know, what a lot of people take to be the strong possibility that Everett isn't coherent. So that's another. But yes, I think if Everett were to succeed, if Everett were to be coherent, there's a well-defined sense in which it doesn't share the non-locality. That is, in order to prove Bell's theorem, you need to suppose that after the measurements are done, there are facts about how they came out. That seems like an incredibly innocent assumption, but it's exactly the assumption that Everett denied.
Maybe you can correct me, but isn't the other thing that the locality criterion requires some stuff happening in space, right?
So
in physical free space, so if there's nothing...
No, but you can ask about, here's what's true on every interpretation except Everett, okay? The sort of, the local density matrix over here changes non-locally as a result of you doing something over here. Okay? That's true on collapse theories. You know, the Bohmian analog of that is true in Bohmian mechanics. It's not true in Everett. Okay, doing something over here has no effect.
But over here and over here, that means these are locations in
Yeah,
space.
you can talk in Everett about the reduced density matrix corresponding to this point in 3 space. Okay, and you can ask whether the reduced density matrix changes over here when you do something over there, and the answer is no.
It seems like funny that you refer to 3 space if there's nothing like 3 space in your theory.
No. This
but I guess you could say it's emergent or
perfectly well mathematically defined.
Yeah, mathematically.
Yeah.
That's right.
Yeah.
So let me just, there's a very nice illustration of non-locality in Bohmian by Rice. Well, actually, David also played out, but also has a nice illustration, but you have to use spin for that. But I don't want to talk about spin, so there's also a nice illustration without spin. So first consider a single particle. Suppose you have a wave packet, and it goes through a beam splitter, so it splits a packet and one packet going up and one packet going down. And there's perfect symmetry, and these packets bounce off at these mirrors, and then they recombine. There's some interference. So this was just on the level of the wave function. What's going to happen with the trajectories is, this is one possible trajectory. It's going to bounce off the mirror, and then instead of going straight through, as you maybe expect, it's going to curl and turn back and turn around. Another possible trajectory is the blue one. We're going to do something similar. It's also going to bounce. So the mathematical reason why that happens is that you have first order dynamics. Okay? So given an initial position, you have a unique trajectory. Suppose this trajectory was just going straight on. Well, another possible trajectory would be the blue one and then going straight down because of symmetry. Again, we have 2 trajectories which cross at the same time. Okay? So initial position, we'd have a fixed initial position at a certain time, and we have 2 possible trajectories. This can't happen. So by that reason, you know this, something like this must happen. Trajectories don't cross.
So in Bohmian mechanics, particles never run into each other?
No, they can't. So this is just one particle situation, right? Many particle situation. If you have n particles, you have this no crossing property in configuration space. In 3-dimensional space. That means in physical space they can still cross.
Okay.
So maybe that's also worth mentioning. So you might think, okay, it is making this funny behavior, can't we measure that? But the answer is no. You're never going to be able to follow this trajectory without changing the wave function. So if you want to measure where the particle is going, you're going to change the wave function and it's going to change its later behavior. Okay? The only thing you will see is that there's 50% chance up or down, and no matter where you're, there's always 50% up or down.
So if you were to draw a family of trajectories, not just 2, none of them would ever cross. Is that correct?
Yeah. So now let's consider an entangled state. So as Lenny can explain, an entangled state, that's a state which cannot be written as a product. Wave function for 2 particles. And it's entangled in the following way. If the one particle goes up in that direction, the other particle goes down in that direction. Plus the state that the particle, this particle on the left goes that direction, and the other one goes up in that direction. What you get is, if you place mirrors on both sides, is you're going to have this funny behavior on both sides. Okay? If I now remove the mirrors on one side, you're going to see that these particles cross here. So this is an example of particles crossing. So the reason they don't cross here is you have to do the argument I just did on the previous slide, put it in the configuration space. The reason why they cross here is, well, remember that I told you have something like effective collapse. So if packets don't overlap in space, get an effective collapse. So here these two packets don't overlap in space. So you're going to have an effective collapse to either this packet or that packet. Either one of the two packets is going to guide part on the left. So this is an illustration of non-locality. So if somebody here chooses to put the mirror here or not, it's going to have another effect on the part on the left. And it doesn't matter how far these mirrors are away from the system on the left. Okay? So now the thing is, can we use that to signal? Can we use that to send signals faster than the speed of light? But the answer is no. And why can't we? Well, if you measure here, I already told you you cannot really follow the trajectory without disturbing the wave function, so the only thing you can do is basically collect the statistics of what you're going to find here. And in this case, if the mirror is in place, is always in place, you're always going to find 50% up, 50% down. It doesn't matter where exactly you measure. If you measure here, here you go find one in the middle, or there, it's always 50 up, 50 down. But the same is true here. Okay? You always find up 50% up, 50% down. Okay? If the mirrors are not there. So also if you want to have some combination of putting the mirror there, putting the mirrors not there, like flip each time, it's not going to matter either. All that you're going to see on the left hand side is 50% up, 50% down. So the theory is non-local, but you cannot use it to signal.
Am I thinking that if the initial distribution is not psi squared, there's no signaling theory there?
Exactly. No.
Okay.
So what is the reason? So it seems to be some conspiracy. You have this non-locality, but you cannot use it to signal what's going on. That's a property of equilibrium. Okay. If you had a non-equilibrium distribution, a non-psi squared distribution, you would be able to signal. For example, if for some reason the wave function is still the same, but we know that all particles go like that, then clearly you can use that to signal, because either all particles are going to end up in the upper side or in the lower side, depending on whether the mirrors are there. And here you can draw the analogy with classical statistical mechanics. Okay. Classical statistical mechanics, you can use heat to perform work. Yeah? But if you're in equilibrium, thermal equilibrium, you cannot use the heat to extract work. So similar here in equilibrium, you cannot use the non-locality to signal faster than the speed of light. So these two properties, these are kind of valid for every theory that agrees with quantum mechanics. Standard quantum mechanics is non-local, as well as any theory that agrees with it empirically is non-local, except maybe in rods. But you cannot send signals faster than the speed of light. Okay?
Or are there any situations, cosmological situations, where you would not expect quantum equilibrium?
It's kind of tricky, right? Because on one hand you would say equilibrium is always is the most natural state. Equilibrium is always what you would expect, so why would you expect non-equilibrium?
Well, I guess.
It's like
Is there
boxes of gas, right? They're always in equilibrium. Is there a reason to expect one box will be out of equilibrium?
Is there a dynamical cosmological explanation for why quantum equilibrium would hold?
You mean if you start from non-equilibrium, why you go to equilibrium? Or?
Sure.
Well, there's investigations like that to see what happens if you start from non-equilibrium. Would it be still a trace of that today?
Yeah.
In cosmological scenarios. Anthony Valentini is doing that.
But I think that, I think the way the theory is usually presented And maybe for this reason equilibrium is a bad word to use. I think the way the theory is usually presented, it's presented that the relationship between the wave function and the probability distribution over the particle positions, which is being referred to here as equilibrium, is just introduced as a fundamental initial condition. And if it's present as an initial condition, then it's very easy to prove theorems that it's preserved over time.
Exactly, or statistics?
Exactly. Well, I mean, it's a statistical claim.
Yeah.
But statistically, exactly, yeah.
Because certainly
Yeah, something like that is true, but it's more tricky than that, right? Because the universe probably didn't start out as an ensemble of systems with all the same.
No. If you need some, in my judgment, you need some kind of Jungian understanding of probability, just like you do in statistical mechanics. You need some understanding of what it would mean to talk about a probability distribution over, probability distribution over initial conditions of something like the entire universe, even though there's only one, universe. That's a problem in foundations of statistical mechanics too. I think there's a way of addressing it there, and I think there's an identical way of addressing it here.
it seems like any deviations from quantum equilibrium or deviations from the Born rule in a cosmological context, if they produce observable consequences, that would be a big deal.
Yeah,
Sure.
but if you want a theory to reproduce there is a version of this theory that reproduces quantum mechanics. The way you get that theory is to introduce equilibrium as an initial condition.
So is it fair to say that non-quantum equilibrium would be new physics beyond quantum mechanics?
Yeah.
In either case?
Oh yeah, for sure.
And people are looking for that. If you start out and maybe it still deserves some. The tricky thing is you seem to go very fast with equilibrium. There's very fast relaxation. So you really have to look at special states where this might happen. Maybe you can find these in cosmology. So the theory I just presented that was actually applicable just for non-relativistic systems, without actual particles. You can extend this theory to quantum field theory. I've worked a lot on that. Goldstone was there, also worked a lot on that. This collaborator. And the state of the art is that for quantum field theory, there seem to be like two possible natural ontologies you can choose. Either particle positions. Okay. Quantum field theory of particles can be created and unrelated, so it's natural maybe to introduce actual particles. Which then can pop into existence or evaporate. Or the other thing is you can go with a field ontology. Call this quantum field theory, so it might be natural to look for a possible field ontology. And the state of the art is that particles seem to somehow work better for fermions and fields for bosons. Okay. And for the rest of the talk, I'll just need bosons, so I'll just focus on that. So just a simple example, the scalar field. Well, actually, Bohm himself in '52 in the appendix of his paper, he already treated the electric field So here, let me consider the scalar field. Okay? This is usual Hamiltonian for the scalar field. And you've seen Matt Johnson's talk, he quantized that using Fock space representation. But for me, to get my Bohmian formulation, I will use the functional Schrödinger picture. So that's another representation of these field operators, phi hat and pi. What you do is something like the position representation in homologistic quantum mechanics. The operator phi hat, you're going to represent it by just a scalar field phi. And its conjugate momentum, you're going to represent it by functional derivative. And these operators are going to act on a wave function. So this is my wave function. It's then a functional on a space of fields. A space of scalar fields phi. So for each scalar field, it's going to associate a complex amplitude. And it has some dynamics.
Ward?
Yeah.
The key idea, one of the absolutely key ideas of quantum field theory is creation and annihilation of particles. You want to change the number of particles. It's absolutely essential. If you can't do that, you're not doing field theory.
Yeah.
I'm not seeing creation and annihilation.
No, but you can formulate it that way if you want.
Yeah, of course
This is an
you are.
equivalent formulation
just
of
checking,
quantum field.
because-
Yeah. Well, you must know, right? In inflation theory, that's exactly what people use. Yeah. And they go to Fourier modes and.
Okay, I wasn't clear on what you mean by an operator.
Sorry.
It wasn't clear to me what you meant by operator.
Okay. So just usual field operators, phi and conjugates, momentum.
Also, of course, you don't want to have, in relativistic theory, this is the non-relativistic theory.
Well,
Is there any problem?
This is a relativistic scalar field, right?
Oops. Ah.
This is Klein-Gordon field. And
Okay, so
this is supposed to be relativistic.
so there's no problem in making a Dirac field or any other relativistic
No,
field.
no. If you want to do a Bohmian treatment of the Dirac field, it's going to be part of positions. Then you have actual positions, can be created and annihilated. If with boson fields, it seems easier to introduce just actual scalar fields. So, and then you also have like a guidance equation. Okay? Something like that you can do for basically any bosonic field. And the thing is, this theory reproduces the usual quantum predictions. Of course, you would have to include fermions, just by Dirac fields, whatever. You have a full theory, right? But you can say that these kind of theories reproduce the usual quantum predictions. And the usual quantum predictions, well, these are Lorentz invariant. So also the predictions of this Bohmian theory, it's Lorentz invariant. But you probably didn't notice this, that this equation of motion actually spoils Lorentz invariance. You need a preferred reference frame to write this equation of motion for the Bohmian scalar field. Okay. So the situation is, on the fundamental level, this Bohmian theory assumes a preferred reference frame. But on the level of predictions, this preferred reference frame doesn't show up. Again, that's because you're stuck in equilibrium. In equilibrium, you don't see the preferred reference frame. On the other hand, you can make the theory Lorentz invariant if you want. And Shelley, me, and some others just this week put out a paper on how you can just change this law in a simple way such that the whole theory is Lorentz invariant. Okay. Yeah.
Does that way of modifying the equation again rely on being in the
So this is going to be again an equilibrium distribution, and in equilibrium you're going to get again the usual quantum predictions.
yes, I was just thinking, as you said a second ago, that the Lorentz invariance depends on the equilibrium.
Oh yeah.
So,
No, so you can formulate the theory in a complete Lorentz invariant way, also on the fundamental level. So you don't assume a preferred reference frame. So now quantum gravity. So all the other usual force fields, they're all quantized, they're all quantum theories. You would expect gravity to also be a quantum theory. But there's even more if you want to have something like Einstein's field equations. What you see is that this metric couples to the energy momentum tensor of the matter. If you quantize the energy momentum tensor, it becomes an operator. You also somehow have to quantize the metric. Okay. So that's the motivation to look for quantum theory for gravity. And the first thing you could do is just do the usual program of quantizing a classical theory. You choose some classical variables and you replace these by operators, like the maximum states, and so on. What you get if you do that, if you follow that approach to Einstein's general relativity is you quantize the metric, so the metric is replaced by an operator. So more precisely, it's going to be a tree metric. It's going to be a metric on a space like hypersurface. And then in the functional Schrödinger picture, you get your wave functional. It's going to be functional on three metrics. And the equations you get for them are the following. So the time derivative of psi is going to equal some Hamiltonian acting on psi. Then the Hamiltonian acting on psi is going to be 0. That's what the width now. Okay. And you have some further equations, some further constraints on this wave function. So you see, you immediately seem to run into a problem, right? The Hamiltonian time derivative of the wave function is 0. So the wave function doesn't evolve in time. So how can we match up with our experience? Stuff seems to evolve in time. The equations don't immediately give you that. From the equations also can we tell whether a universe is expanding or not? This is not so clear. So this is the problem of time. And as Jean-Carl mentioned, I think one of the major approaches is to identify within this Hamiltonian some variable that could act as time. So you want to identify in your world some clock variables and express the other variables with respect to that clock variable. Of course, you again have the measurement problem here. That's maybe more severe than in the usual context, because here we're talking about the whole universe. So there is no measurement device outside the universe, there's nobody observing the universe. So how can this wave function collapse?
If we're going to try to find one of the coordinates to treat as time, should we be using 4 metrics instead of 3 metrics then? Having
Why would that help?
What was it?
Why would that
Well, because we seem to observe 3 spatial dimensions and 1 time dimension, so if we're going to have h psi equals 0 and we're going to try to find something in there to look like time, we better have 2 things left to be space. So,
yeah, I don't see. Well, I can just tell you where this 3 metric comes from. That's first they write general relativity in Hamiltonian formulation. Okay. In Hamiltonian formulation, you assume some space-time splitting. And what seems to happen is that you can describe it as a 3 metric evolving along space like hypersurfaces. When moving on space like hypersurfaces, it's somehow like evolving in time. But I don't know, there's a lot of work on identifying suitable variables, and there are some toy models, but I don't know what the status is of that. I think it doesn't go further than just on toy models of how it could work in some specific conditions. And the other worry is here, the third one, worry is that what's the meaning of space-time diffeomorphism invariance? So in general relativity, it's invariant as a space-time diffeomorphism. So smooth invariants under different choices of coordinates, which are related to one another in a smooth way. This equation actually expresses the fact that this function of psi is invariant if you apply spatial diffeomorphisms to the metric, to the 3 metric. But that's an equation that doesn't say anything about time-like diffeomorphisms or space-time diffeomorphisms.
Is that fundamentally related to why, because in Bohmian mechanics the position basis is preferred, that the ontology is all based on positions of particles?
What is related then? The fact that you don't have diffeomorphisms?
That you're only talking about spatial diffeomorphisms, not space-time.
Well, this is just ordinary, I haven't said anything about Bohmian, right? This is just ordinary grid equation. It's just a puzzle. Because you think space-time diffeomorphisms invariance is some building principle for Einstein general relativity. So what happened to that? Did you throw it away, or is it still somewhere there? It's unclear.
Okay, I mean, so you haven't made the connection at all between Bohmian mechanics and this stuff.
No.
But could there be a connection?
No, I'm going to say something about Bohm, of course. The thing is with Bohm, you can solve the first 2 problems, and the third problem it seems clear. Okay. If you're most invariant, that seems unclear. Well, what you can do is have a Bohmian theory where you have, again, apart from the wave function, you also have an actual metric, a 3 metric, and it evolves according to some sequence of hypersurfaces. So the thing is, for the metric is going to evolve in time. So you're going to have the emergence of time again. Okay. Of course, here you don't have a measurement problem. That's the same one. And the third one is that diffeomorphism invariance. Okay, you know what it would mean again. You have again a space-time metric. You have diffeomorphism invariance. Can you make a diffeomorphism of the space-time metric and get a new solution for irreversible motion or not? In the more simple way of formulating that dynamics, you don't get space-time diffeomorphism invariance. Maybe you can resolve it. Chris?
Do you get the same evolution if you pick a different slicing?
No. That's exactly another way. So you get foliation independence. That's another instance of having not having space-time diffeomorphism invariance.
Ward, you know, in simple cases, where you look at you know, in simple cases, in first quantized cases, yeah, there will be evolution of Bohmian particles even when the wave function is in an energy eigenstate or something like that. But usually the evolutions are pretty uninteresting and pretty restricted. Is there reason to believe that the evolutions here are going to be genuinely interesting ones? Are going to be ones that look like what we see?
Well, a lot of models have been worked out in this case. A major figure is Nelson Pinto-Neto.
Say it again?
Nelson Pinto-Neto. It seems, yeah, you get interesting stuff out of it.
There's reason to believe that you're going to get stuff like
yeah,
what we see.
You can't say the universe is expanding or contracting. They studied mainly simplified models, mainly superspace models. Basically you have a scale factor and just a scalar field. Everything is homogeneous, isotropic.
But I mean, there's a prima facie worry, right, from the simple cases that we know, that the kind of actual evolution we can get under those circumstances is very restricted. Is there some way to stop being worried about that? Or is there some sort of general remark one can make that takes away such worries?
I can't, just can point to these examples.
Okay, right.
But indeed, there might have been this worry.
Right, right, okay.
People, for example, for the Wheeler-DeWitt equation, for the Hartle-Hawken wave function, you get trivial dynamics. The metric just stands still.
I see, right. Okay, so it
that
sounds
was
like
wave
there
function
are
of
in
the universe.
principle some worries like this.
But then if you Hartle and Hawken themselves, they assume some decoherence. You have two packets corresponding to an expanding universe, corresponding to a contracting universe. And then for the Bohmian evolution, everything works out nicely again.
I see.
Is an issue with problem 3 something that people think might be pointing towards the idea that maybe there is a preferred time coordinate in quantum gravity? That there is a preferred location?
Yeah, people are investigating that. I don't know.
Because certainly coordinate invariance is the sort of bedrock of general relativity, and that it would be very interesting if that was not preserved in a full theory quantum gravity. But that's an open question. Okay.
The other thing I forgot to mention here is that, so if you just consider gravity alone, you can tell whether or you can at least consider the question, is the universe expanding or not, okay? And you can also derive time-dependent wave equations. If you consider also matter, for example, you describe it by a scalar field, so you have the matter and the metric. You can look at this conditional wave function for the matter. So what you do is take the wave function of the universe and plug in the actual metric, wave function of the universe, plug in the actual time evolving metric, and you might get a non-trivial time dependence.
But so that suggests a more precise version of the question I asked before. For example, if you have the matter and the metric here, are you going to get evolutions that satisfy the Einstein equation? Is that you know?
Well, you're going to get the classical limit, so you're asking more.
Yeah. In the Wheeler, you know, in the H is identically 0 state.
In which case?
you know, you have this equation that H is identically 0. Okay. In the states that allows, so there's a well-defined question. Yeah, in the states that allows, you can solve for the motions of the matter and of the metric. Okay. Are they moving in a way that counts as a solution to the Einstein equations?
Well, in general, not. There's going to be always quantum corrections. So
No. I mean modulo quantum corrections.
Well, in certain cases, you would expect that, right? Because
but I mean, this is exactly what, you know, because the constraint that you're in that the wave function is an energy eigenstate, like we said, is going to put very severe constraints on the kinds of motions, okay? And I take it it's going to separately constrain the motion of the metric and the motion of the stress energy tensor. It seems like there's a question whether those constraints separately are going to be consistent with their being related to one another in the way that the Einstein equation specifies.
So I didn't follow the last one. You have two kind of constraints? You only have
No,
one.
but you have a constraint on... You
the
have
the constraints coming from classicality.
Right,
yeah,
right,
okay.
right.
Well, again, so...
I mean, because, look, there's a whole other strategy I take that one could take. Wait for people doing ordinary quantum gravity to solve the problem of time in some other way, okay? And then Bohmize that, okay? And that's going to work out in a trivial way, okay? That's going to be fine, okay? The question is whether Bohm can actually solve the problem of time for us, okay? And clearly, it's not enough to say you solve the problem of time to say there can be evolution.
Sure, you have to check
it has to be the right kind of evolution. And so that's what we're talking about.
Again, for having like a reasonable time evolution for this type of wave function, this conditional wave function, again, I can only refer to examples where it works out.
Right, okay, okay.
And something like this is close to what people outside quantum mechanics do in ordinary quantum gravity.
Right.
But the only exception is that they put in a classical free metric.
Right. Okay.
Of course, in the classical paradigm, you have no reason to do that. It seems like a funny trick. Well, why would you do that?
Right. Here it's perfectly
Again, it's perfectly natural.
Right.
And again, this guy Nelson Pentoneta has worked with collaborators, has worked out a lot of examples, and of course you have to assume some simplifications always, some approximation.
Right.
It seems to work out nicely.
Good. Okay. Thank you.
I'm trying to understand the second point under solving problem 1. And so you're saying that you can derive the time-dependent Schrodinger equation for the conditional wave function. So what I'm hoping for there is that you can show why the QFT evolution of the wave functional falls out from your Euler equation. And
what you want to get out, nothing has shown rigorously in all generality, right? It's like something disobeys the usual quantum field theorem perfect space-time. So.
Okay, but when you say we can derive, you haven't derived in full generality.
No. We can in principle derive.
Okay, good. And then on the right-hand side, I'm worried because what I want to show is that, look, quantum field theory in Minkowski space, the kind of thing that we were doing before we started adding in gravity works. And in that case, G3 of T could well be constant, right? And then there'd be no time dependence at all on the right-hand side of the equation. If we just had a static metric. Or am I confused? Yeah. I would have thought fields could do interesting things even when the metric was static, but the right-hand side suggests
I don't know the answer.
Not possible. Okay.
But wait, I don't understand. We do have, for a long time, a formulation of Bohmian mechanics for flat space relativistic.
Sure, you want to have a
come
out of
so there isn't a problem about that. I guess the question is whether this reduces to that.
Yeah, that's exactly the problem. If this is a Minkowski metric, you don't have time dependence, so how can you do that?
So there's, but so is that, is that something to worry about?
Yeah,
because
I don't know the answer, so I guess, I don't know the answer.
Okay.
So earlier you showed that when you're formulating Bohmian mechanics and putting it in a quantum field theory perspective, you don't naturally get Lorentz invariance. The default is that there is a preferred frame.
Yep.
And
And that's the simplest way to formulate.
No, but you do naturally get Lorentz invariance of the statistical predictions. You do naturally get a theorem that the identity of the preferred frame can't be detected by any possible experiment.
Okay.
That falls right out.
Sure. But you've, in recent work you were saying that you worked to formulate in a way which is Lorentz invariant and which does get rid of the...
In the Minkowski spacetime.
Hmm?
In the Minkowski spacetime. So it's about Lorentz invariance. It's not about general invariance.
So it's extending that. If you formulate it in a Lorentz invariant way, have you also investigated if that sort of trades off and gives you a preferred time foliation? Because you don't have a preferred spatial frame anymore.
There is something like that in there still, preferred foliation. But probably I shouldn't go into that all too much, but no, I shouldn't go
Actually,
into that.
since you spent so much time on this, let me ask a sort of subtle question that you may or may not have thought about. So everyone who does quantum field theory learns that even for gauge fields, you have to break Lorentz invariance.
You have to break Lorentz invariance?
Absolutely. Anybody who doesn't know that hasn't learned the theory. In order to do gauge, there are only 2 degrees of freedom in the abelian gauge field, in other words, electromagnetism. You can eliminate one, d mu a mu equals 0. To eliminate the other one requires breaking Lorentz invariance. Well known, standard stuff. Here's the subtle question.
It's an anomaly or something.
It turns out that to prove the Goldstone theorem, which was done by Goldstone, Salam, and Weinberg, you actually have to state explicitly that the theory has explicit Lorentz covariance, i.e. you cannot break Lorentz invariance. Now, this is the reason that the Higgs trick works. See, you would have thought from the Goldstone theorem that the Higgs boson has to be massless. But the reason it's not, and that it basically, the way the whole Higgs thing works, is that that theory, it's the theory of an abelian or non-abelian gauge field, explicitly breaks Lorentz covariance. You cannot quantize the theory without breaking Lorentz covariance. And therefore, this actually has very strong implications. Namely, it means that the Higgs trick is possible. Okay, well, so the question is, since apparently you have to break explicit Lorentz covariance, though in this mild way, in your version of the Bohm theory, does that have really important implications? Like it invalidates the proof of the Goldstone theorem, and so that opens up a whole new channel for physics possibilities.
Not immediately that I can see.
Okay, well, if you didn't know about the gauge field story, then you'd have to go back and learn that stuff. But that's actually, I think, your discussion sort of reminded me of that interesting. I mean, this is really fundamental for modern quantum field theory. This is the whole basis of the electroweak symmetry breaking, and then the general, the so-called standard model of particle physics, which is based on the Higgs trick.
I don't see how Bohm could possibly have an effect on this. The way you Bohmize quantum field theory, exactly as in the first quantized theory, is that you solve the equations. You solve the equations for the quantum state exactly the way you do in the standard theory. It's only after you have a solution in hand that you apply the guidance condition and determine the motions of,
well, the question is
of the vehicles. So it's not, so anything that emerges in the standard solution is going to automatically emerge here as well.
Well, one might have thought similar things about gauge theory, except it doesn't work.
No, it's not the same thing.
Okay, well, you may be right. Maybe there's a trivial answer to my question.
Let me just move on. This is not worth working. So this is what work I'm doing right now. So if you want to know more about the stuff about quantum gravity, there's Goldstone work on that. There was it before, Quintonito, all people. What I'm actually interested in right now, and that's part of what I'm working on, is is some kind of new approach to semi-classical gravity. Okay, with usual quantum gravity, apart from these conceptual problems, which one might solve, we also have technical difficulties. It's hard to solve or to find solutions to the relative equation. And particularly, you cannot do perturbations with it. Usual perturbation theory doesn't work. It's not normalizable. So for that reason, people often go through semi-classical approximations, where they treat gravity still classical. Treat matter quantum and treat gravity classical. For example, what they do in the case matter is described by a scalar field is you have quantum field theory on curved space-time. There. So we have a wave function for the scalar field. Matter is described classically. And it's coupled to this quantum scalar field by this expectation value over there. And this approach is going to be okay if the state of matter is approximately classical itself. But if the state of matter is in a superposition of matter, say matter being here and matter being there, if you take the expectation value, you're going to have two contributions to the energy density, one lamp over here and one lamp over there. And that's not what you would expect to have in some more fundamental quantum gravity, because these lumps of matter are going to start gravitating each other. What you would want to have is a lump of matter here with its gravitational field, plus, so in a superposition with, lump of matter being there and its gravitational field. And yeah, now the main idea I'm working on is maybe you can have better semi-classical approximations based on bone. Because in bone you also have to do the Bohmian approach to the scalar field. You also have an actual scalar field. Okay? And this actual scalar field is going to define itself an energy momentum tensor. So why not plug that energy momentum tensor into the classical Einstein field equations? And this problem I just mentioned of having this macroscopic superposition of matter being here or here, you won't have that problem. At least not that one, because the Bohmian scalar field is either going to be here or there. Okay, so the energy momentum tensor is either going to be here or there. So with this Bohmian approach, what I would attempt to do is to have a more fine-grained approach. The usual approach, you take an expectation value, so you do some kind of averaging. In the Bohmian approach, you don't do this kind of averaging. Okay? So you might expect a better approach. And then the idea would be to apply that wherever people use that. For example, it might be useful to consider that inflation theory. More about that in a second. But the only thing is, just applying naively what I just said doesn't really work, because if you just take the usual, what you would expect with the energy momentum tensor for this Bohmian field, it's not covariantly conserved. Consistency of the equation of motion requires that it is. So you need to do something about that. And the thing I found is that you actually need correction terms, and these correction terms you can derive. You can derive from knowing kind of what exactly these correction terms should be in some simple cases. I want to get to the end of thoughts, I'm thinking about skipping some stuff. So you could do something similar in non-relativistic quantum mechanics. You could consider one quantum particle interacting with a classical particle. And you could consider the usual semi-classical approximation, where you have quantum particle described by a wave function, psi, and a classical particle described by position and satisfying something like Newton's equation. But the force acting on this classical particle is by some average over the quantum particle. Okay? That would be the usual thing to do. Now you could also consider some Bohmian semi-classical approach where in addition to the wave function for the quantum particle, you also have an actual position for the first particle. Okay? And you could consider the force on this classical particle to depend on the position of this quantum particle. Okay, so in the usual case, you have back reaction through this wave function. The wave function acts through some average force on the classical particle. In the Bohmian case, it's the actual position of the Bohmian particle that acts back. And the interesting thing is, some quantum mechanists have already considered this Bohmian semi-classical approximation. And what they found is that it actually gives you better results than the usual approach. So we considered a whole series of situations, and they either found better results than the usual one or just equally good results as the usual one. So this is very promising then if you want to apply it to some domain of quantum gravity, if you want to find some quantum gravity corrections. Maybe Bohm can give you something more than what people usually do. So in this sense, Bohm could be used as a practical tool. So although Bohm gives you the same results as usual quantum theory, if you consider full quantum theory, you might use it as like a practical scheme to calculate some stuff you wouldn't otherwise calculate using ordinary quantum mechanics. Let me not go through the details of this picture for time being. We also mentioned that, like, also in many body simulations, some people have found that Bohmian mechanics could be useful for actual calculations. If you want to calculate many body systems, if you want to do that fully quantum mechanically, it's going to be a mess because this wave function will be highly entangled. What you can do is have some approximation based on Bohm, which reduces the complexity of the problem and which gives good results. So the interesting thing is, what I want to mention is this usual Bohmian semi-classical approximation. You can derive it from the full quantum theory. I'm not going to go through the details, but basically what you use is this conditional wave function. Again, you know the wave function of the subsystem, and you can see what equation it satisfies, and then you can, that way you can find a semi-classical approximation from a full quantum approximation. And that's what I, for example, applied to scalar reactor dynamics. We have a scalar field interacting with a potential. So you have a scalar quantum field. And then you have the potential satisfying classical Maxwell's equations. You have the usual Bohmian current, but this one is not conserved. But what you find is you find some extra current, which makes the total one conserved. So you can derive what the correction terms are. And the reason I could do that is in quantum electrodynamics was that I could eliminate gauge. Without eliminating gauge, I don't really know what to do. So I can, in gravity, the same thing is going to be true. I will be able to fix this problem that the energy momentum tensor is not conserved, but I would have to eliminate gauge somehow. And that's more difficult in ordinary quantum gravity. Because gauge is diffeomorphism invariance, how to eliminate diffeomorphism invariance. That's a hard problem. Anyway. In simple cases for quantum gravity, you can do, you can eliminate gauge. For example, if you assume complete homogeneity and isotropy. Okay? And these are some equations. How to do. I won't go through them. The thing I'm working on now is to see if I look at inflation theory, which is just assuming perturbations on top of homogeneity. Am I going to be able to predict some quantum gravity corrections or not? That's work in progress. So I'm rushing a bit because I want to get to the final thing of my talk. That's what was discussed earlier. That is the problem of the quantum to classical transition in inflation theory. So just first one slide with the structure. What is the structure of inflation theory? Well, you have an inflaton field, fine, and you write it as like a background field, which is homogeneous, sensation invariant, and some perturbation on top of that background, delta phi. And the same for the metric. You write it as a Friedman-Walker metric, plus some perturbations, given by phi. So the background here is just described by the scale factor. The universe expands or contracts. All you can do is combine these two perturbations, delta phi and this phi, into one perturbation. And that one is gauge invariant, so it completely captures all the perturbations, all the scalar field and the metric. So in summary, you have three variables. The scale factor, the background influence field, which is homogeneous, and then some variable describing the perturbations. What people usually do if they consider inflation theory is they keep this background classical and they just quantize these perturbations. And they assume these perturbations move in this background scale factor and homogeneous scalar field. And the quantum state they use for this for these perturbations is the Bunch-Davis vacuum. This is the setup of inflation theory. All the other fields, all the other wrinkles, these are just wrinkled out, ironed out because of during the inflation. So the only thing you have left is these quantum fluctuations for the variable y. And these quantum fluctuations, what do they give you? Well, in the end, these are the fluctuations that give rise to the fluctuations in the temperature of the microwave background. They also give rise to large-scale structures such as galaxies and clusters of galaxies. So these quantum fluctuations, these vacuum fluctuations, they're described by a vacuum state, these vacuum fluctuations, these act as the seeds of all structure in space. But the problem is now the following. So these vacuum fluctuations, these are described by a quantum wave function which is homogeneous and isotropic. It's invariant under translations and rotations. Okay? But obviously these galaxies and microwave background, this is not uniform isotropic. So somewhere we have to break that symmetry. Somewhere the symmetry of the wave function has to be broken. Okay? Or to put it differently, you have all these quantum fluctuations, you assume these are just tiny fluctuations, just fields fluctuating back and forth. At some point you assume that these become classical. That's, for example, what people do in structure formation. At some point early on, they assume the quantum fluctuations become classical. Once they become classical, they can use the usual series of structure formations to explain galaxies and so on. So the question is, how do you get from the symmetric state to an asymmetric state? Well, in usual quantum mechanics, this must have happened through collapse of the wave function. Okay? At some point, collapse must have occurred, which breaks this homogeneity in isotropy. And that's why you get to non-homogeneous states. The thing is, what exactly would cause this collapse of the wave function in the early universe? And there's no such thing as measurement devices or observers around, so what could cause that? Okay? So this is again the measurement problem. Okay? But a bit worse because we're in a cosmological context. Possible solutions, well, we've already heard data talk about that. You can consider this problem from a variety of perspectives, from collapse theories. Daniel Sidorsky is working on that, and Rhodes, Bohmian mechanics.
Yeah, sorry. I'm just a little confused about what we mean when we say, just quoting your phrase there, measurements in the early universe. Like, what? Measurements? I mean, that's the point. Yeah, that's the point. It's like, what would, you know, right? I mean, that's the point that Bell even made. Right? This was just in general in quantum mechanics. This was a weird term. So I get the, but are you just, this is an open question. We don't know exactly what's going to replace this notion in cosmology.
Well, you know, you're gonna have to go through one of these theories that solves the measurement problem. You know that, right? And in recent cosmology textbooks, people acknowledge that Little and Light, Nonfinal, they acknowledge, okay, we have a problem, it's an instance of the measurement problem. you have to go beyond usual quantum mechanics to solve that problem.
And I understand how the decoherence picture doesn't solve the measurement problem. You still have a superposition. But in the decoherence picture, things that we usually thought about as measurements are not special things. They're just physical interactions of systems. And that it certainly makes sense to think about that happening in the early universe. You don't need observers or measurement apparatuses like in a laboratory to happen. But would you say that so that's not what you're focusing on. What you're focusing on is that you still have the basic quantum measurement problem underlying everything.
So, of course, I agree with you. And that's reasonable to look for decoherence in the early universe. And if you have decoherence, and you can say, okay, as soon as I have decoherence, then I collapse the wave function, or then I'm in a Ross situation. Well, and a lot of work has focused on that. There's a huge body of literature on that.
Because if you have
Let me
decoherence,
immediately say that this is kind of difficult. So what happens is people are looking for people are looking for sources of decoherence. Okay, where could sources be? So I've just given you have this background, this fluctuation of the background. Where are the sources for decoherence? One idea is, okay, this might come from other fields, usual matter fields coupled to these fields, to the fluctuations and the interactions cause decoherence. Another thing would be like, this is just first order perturbation theory. If you look at higher order perturbation theory, higher order corrections to the dynamics might cause the decoherence. But I think it's fair to say that it hasn't been actually solved. People are just guessing where the decoherence might come from. And I think it's also fair to say that people only have constructed toy models of what the interactions could look like. And the question is, when does this, so the first question is, does the decoherence happen? And does it happen early enough? For example, you want it to happen early enough that where people usually treat the perturbations classically, that you can really assume these perturbations classically. If it happens too late, say, when you look for our telescopes, it will be too late. It can be certain. You have a strange history of the path of the universe.
is the thought that the decoherence would kick in towards the last few evols of inflation?
Yeah. So you have these what is happening is the physical modes start inside the horizon, and during inflation it gets stretched outside the horizon. Okay, they get amplified, as they say, and that's the point, basically, where you would expect classicality to occur.
So you're saying that you think all this happens in the phase when the universe is absolutely acausal, where nothing can happen, because nothing is in causal contact? That's what you just said.
That the classicality
Once
happens.
things move outside the horizon,
Yeah.
according to the standard picture, nothing happens.
Yeah.
You think that under those circumstances where no causality can act, somehow decoherence occurs?
I don't know what could happen. People want the classicality to happen by the end of inflation. That's all I know people say. Well, that one doesn't really matter. And I know that, for example, in the Bohmian description, that happens. Once modes go outside the horizon, once they're there, they're going to evolve classically. From the Bohmian point of view, once they're outside the horizon, they're going to be evolving classically.
Joel, your question's a good one, but it relates to these fundamental questions about horizon complementarity, black hole information loss, and the question of whether or not you can think about decoherence in the normal way when you're talking about horizons. And you certainly have that during inflation. So I understand what you're saying about it being acausal, but there's a lot of open questions as far as how you actually get decoherence in a situation like that.
Some people claim that there's decoherence for the modes outside the horizon coming from the modes inside the horizon. I'm not a specialist in that, but that's what I think a whole bunch of people claim that happens.
I mean, this is because quantum mechanics is non-local.
No.
Is that the reason?
I mean, this is the decoherence happens from entanglement. So
So you have entanglement between the
Sure,
modes
that's true. But
inside the horizon and those outside the horizon. That's what
but
these
look,
guys are.
I think, Ward, there's something that I know you're aware of that maybe you didn't emphasize enough in answering this question. First of all, the business that, you know, for the purposes of what we're talking about here, solving the measurement problem is exactly the same thing as explaining how the initial symmetry gets broken. Okay, how you develop fluctuations here as opposed to here, or something like that. And the statement that the correct statement that decoherence can't by itself solve the measurement problem is equivalent to the statement that decoherence can't by itself break the symmetry. Okay, so decoherence by itself is going to do nothing here. Decoherence is a crucial element of every genuine strategy for solving the measurement problem. And once the symmetry gets broken, decoherence is going to come in and preserve the way it's been broken and prevent reinterference and so on and so forth, and it's going to be crucial to the discussion of the growth of these fluctuations. But as to the question of breaking the symmetry in the first place, the measurement problem and the problem of breaking the symmetry here are completely equivalent, okay? And the arguments that decoherence won't solve the measurement problem are going to be arguments that decoherence can't break the symmetry here. Decoherence is something that's happening in accord with the unitary linear equations of motion. It's not going to break the symmetry, okay? You need one or another of these solutions to the measurement problem to break the symmetry. Once you have that, decoherence is presumably going to play all kinds of crucial roles in shoring it up, in preserving it, and encouraging its growth, so on and so forth. But the initial breaking of the symmetry, the questioner rightly said, decoherence can't solve the measurement problem. That's mathematically equivalent in this context to saying decoherence can't break the symmetry.
Is it possible?
But I didn't say that, right?
What?
I didn't say that.
No. I know that you know. You didn't. I'm worried that you didn't emphasize it. No. Of course. No. This is not contradicting anything I said.
Is it possible that the expansion of the universe itself is what fundamentally breaks the symmetry?
Not if the expansion is something occurring in accord with the unitary equations of motion. Those are going to preserve whatever symmetries were present in the initial situation. They're not going to introduce any new symmetries. Okay. The only way they're not going to introduce any new asymmetries. Okay. The ways asymmetries get introduced is, for example, in a theory like GRW, the place where the collapse occurs is random. Okay. That can break a previously existing symmetry in the wave function. Or in Bohm's theory, the actual locations of the particles or the values of the field theoretic variables are randomly arranged. That can break a symmetry that's implicit in the wave function.
If you have the Bohmian picture in a cosmological context, then the effective cosmological horizon singles out particle configurations. So that's the kind of thing I'm talking about, right, to break the symmetry.
Right. Exactly right.
So I was going to illustrate the problem and possible solution that in like some simple analogs I was going to go into inflation terms. I think there was two simple cases I was going to discuss, like just a decaying atom, which emits a photon and with spherical symmetric wave function, and the inverted harmonic oscillator. Especially this one has a lot of features that the Nonfinal theory has. So it might be all too simple now. Going through that to the example of the decaying atom again. So assume you could compare it like a decaying atom. It emits a photon. The wave function is spherically symmetric. Okay. So if this is my whole universe, there's nothing is going to break the symmetry. Right? What usual quantum mechanics would say, I also have some detectors placed around that. As the wave function reaches detectors, there's going to be a collapse. to one of these are going to be, right, so you have collapse of the wave function, that breaks the symmetry. That would be the usual story. In a Rolls picture, you would say, if you have, in Rolls picture, you would say if you have just the spherical wave, nothing would break the symmetry, and it would be basically one world, I think. It's completely symmetric. With the detectors in place, a mini Rolls guy would probably appeal to decoherence, would say, there's going to be some decoherence caused by these detectors. I'm going to be able to say that my wave function is a superposition of all these microscopically distinct states, okay? And these corresponds to different worlds. In each world, a different detector fired. In the Bohmian case, what's happening in the Bohmian case is that there's going to be also an actual trajectory of the particle. There's going to be an actual photon trajectory. So even if there's no detectors, there's going to be a photon trajectory, and the symmetry is going to be broken. If there's detectors, what these detectors are going to do is just detect where the particle ends up. So, what was happening, just to make the story short, so we can all go for a break. What's happening in inflation theory is, in the Bohmian case, is something similar. You have the symmetric state. What you see for the actual Bohmian field is that the actual Bohmian field is going to break the symmetry. Okay. And you're going to see it's going to behave approximately classically whenever you would expect it. Once these nodes went outside the horizon, then they're going to evolve approximately classically. And then you can apply your classical theory to them. People have also looked at collapse theories. They're trying to find collapse models where you can see if you apply some collapse mechanism, if you get the right predictions for the spectrum and so on. A large number of people, several groups are investigating that now. In a mini Rolls picture, what you would need to do is look for this decoherence we already talked about. And then the problem is, where exactly would it come from? Can we have a serious model? With some hopeful suggestions, but a lot more stuff needs to be worked out. In the Bohmian case, it's actually really simple. Just a one-page calculation. Look at the actual evolution of the fields corresponding to the fluctuations, and you see whether it becomes classical or not, and you see it behaves classically in a right way. So in this case, you didn't appeal to decoherence. Okay? So that's a nice thing, you didn't need to go through hard calculations to see you get this classicality. If this decoherence, that won't destroy the result. This decoherence is going to preserve these results. So like with many Rolls, I don't know if this is a serious worry, but the worry might be that maybe this decoherence sets in too late or something. I would for sure expect some decoherence at some time, but maybe this happens too late, and you get like a funny history that you get like a funny story that you can tell about the history of the universe.
Just to clarify, in the Bohmian picture, you still talk about decoherence.
You can, yeah. In certain cases, yeah. In both
saying
cases, you often talk about decoherence.
You're just saying that you don't need to appeal to decoherence specifically to talk about a case like this.
It's like having like just universe with a single photon.
Yes.
I didn't, because to talk about decoherence, I could still say, I have a trajectory of a photon and it was approximately classical.
Ward, can I comment on that? I mean, you don't need to talk about decoherence here in order to say how the symmetry is broken. You do need to talk about decoherence in order to say how that particular microscopic breaking of the symmetry is going to be stabilized, is going to lead to larger scale breakings of the symmetry. And in general, in Bohmian mechanics, you need to appeal to decoherence in order to explain how it is that collapsed wave functions stay collapsed and don't re-interfere, and so on and so forth. So decoherence plays a very crucial role in the Bohmian solution to the measurement problem. It's just that it's not the thing that initially breaks the symmetry.
Okay. So I've been told that Bohm was actually the first person to really sort of put his finger on the ideas that became the modern understanding of decoherence. If you look deeply into some of his earlier papers.
That's interesting. And I didn't know that. And that's interesting. It's certainly necessary to the success of Bohmian mechanics as a solution to the measurement problem.
I was just going to ask you to, you might have just said this, maybe just went by too fast, how the Bohmian mechanics in the paper you mentioned compares to the normal, more hand-wavy account where you say you have the fluctuation modes are stretched, horizon, exit, re-entry, so you say that there's fluctuation modes get stretched.
But it's get a squeezed state, right?
Yeah.
That's what people usually say, the state gets squeezed. I was going to go through that in detail, but
Okay.
or maybe just mention the essence. So the squeezed state, what is it? Well, you get a state that it's, if you look at its distribution, it gets like very narrow in one degree of freedom, but very elongated in another degree of freedom. Okay. So if you look at position and momentum space, say at the Wigner distribution, you're going to see that this Wigner distribution gets really stretched out. Remember this picture? For the upside down harmonic oscillators from Carol talked about, you get this stretching out of the phase space distribution. It gets elongated in a certain direction. Same thing happens in quantum theory. When you look at the Wigner distribution, it gets stretched out. And some people claim that this is enough to get classicality. But this is very far from a classical state. Right? What you would imagine a classical state is some state that is peaked in both position and momentum. When space peaks a certain amount of time. In this case, this is completely not true. In the case of the upside down harmonic oscillator, you get actually an infinite stretch, a very big stretch in position and momentum. So it's completely aclassical.
If you have a very precise position in Bohmian mechanics, but a very uncertain momentum, that's not something you think about as
On the level of the wave function? Or
on the level
on
of
the level of
the
the
vehicles.
ensemble? Because the actual configuration always has a different position and velocity.
And a definite momentum.
And a different momentum.
Well, not momentum operator. Depends what you mean by momentum. It has a definite position and the rate of change of its position is definite.
That's why I said velocity first.
Right. But it's not the case that the mass times the rate of, that the mass times the rate of change of the position is what you would get if you did a standard quantum mechanical momentum measure.
So I guess what I mean then is if you have a precise position only in a certain state, is that classical according to Bohmian mechanics?
No.
It also has to have a precise momentum or velocity.
You talk about classicality in Bohmian, the time evolution is basically governed by like, the classical equations. In this case, we have a field equation. If the field approximately evolves according to the classical field equation, you say, okay, I've achieved classicality. Because usually it's going to behave in a quantum way, and behave completely aclassical. So the summary just for this quantum to classical transition is in Bohm you have like a simple way of explaining classicality. And what most cosmologists write about is classicality. Sometimes it's almost as they have like something like a Bohmian picture in mind. Right? So you can use a lot of what they say and just in the context of Bohm you would have to change very little. So you get an easy sort to get to the classical limit. Classicality. In many worlds, you might have to do more work to get there. Probably can do that. Okay, so let me stop here. Thanks.